All right, so Chapter 7 deals with chemical naming, and we're going to be able to take a chemical formula and build it and then name it. So a chemical formula in and of itself is the relative number of atoms within a chemical compound. The relative number of atoms. And so when I say it's the relative number of atoms, that tells us basically the ratio of carbon atoms to oxygen atoms, or sodium atoms to chloride atoms, or whatever. It tells us the ratio of those things, okay? And so when we're dealing with chemical formulas, sometimes we're going to deal with the most reduced version, and sometimes we're not, okay? So these would be examples of chemical formula, NaCl, right? The relative number of sodium atoms to chlorine atoms are 1 to 1, right? It takes one chlorine atom to balance one sodium atom. Would you agree with that? Based on this formula alone, right? One sodium and one chlorine. Okay. Another chemical formula might be MgCl2, right? So what's the relative number of chlorine atoms to magnesium atoms? 2 to 1, right? You need 2 chlorine atoms in comparison to 1 magnesium atom. So these are examples of chemical formulas. Water is a chemical formula, right? H2O, carbon dioxide, carbon monoxide. Those are all examples of chemical formulas. Okay? So let's get out your periodic table of ions, and we're going to review a couple things, and we're going to see where these charges are coming from. Where do these charges come from? They're not arbitrary. They mean something, and they have to do with the electron structure of each individual element. Okay? So I want you to look at the patterns that you see on the periodic table of ions. Okay, let's review a couple things. In the periodic table, we have groups and we have periods. So which way do groups go on the periodic table? Do groups go side to side, or do groups go up and down? Up and down. Groups go up and down. So when we label our groups, right, this is group 1, group 2, and it labels it all the way across. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18, right? The transition metals don't tend to follow rules, so we don't spend a whole lot of time worrying about the transition metals, right? These guys in here. But they are still numbered as part of the groups, okay? So we have groups 1 through 18, or 1 through 8, if you leave out the 10 groups of transition metals, okay? All right, so what I want you to think about that matches their group number, okay, group 1 contains 1 valence electron. Do you remember what a valence electron is? What's it mean to be a valence electron? The outermost shell. Okay, so let's review here. Is this, I always abbreviate electrons with just that E minus. Okay, so a valence electrons are outer shell electrons. Okay, these are the ones that are available for bonding. Okay, these are the ones that are available to bond with other atoms. Okay, so the valence electron numbers match their group number. Okay, so that means group 1 has 1 valence electron. Group 2 has 2 valence electrons. Okay, we skip the transition metals. Group 3 has 3 valence electrons, or group 13. Group 14 has 4 valence electrons, 5, 6, 7, and 8. Okay, so the trend you see is that their group number, essentially, right, disregarding these transition metals, matches the number of valence electrons, or electrons they have available to bond. Okay, does that kind of make sense? You see that trend on the periodic table. So group 1 has 1 valence electron, group 2 has 2, 3, 4, 5, 6, 7, 8. Okay, the transition metals in the middle don't quite follow the rules, so we don't include those in that pattern. Okay, so I want to think about if group 1 elements like hydrogen. Okay, so I'm going to draw just like a kind of inaccurate version of hydrogen. Here's hydrogen, right? Hydrogen has 1 outer shell electron. Okay, it has 1 outer shell electron. That's it, because it's in group 1. So it has 1 electron available to bond. Are we on the same page with that? That's what a valence electron is. Okay. what does an electron, or what does an atom want to feel complete? How many electrons does it want? Do you remember? Electrons want how many electrons to fill their shell? They want 8 electrons. Okay, they want 8 electrons. All atoms want 8 electrons. Or what they want is a full shell. Okay, in order for them to feel happy and complete and whatever, they want 8 electrons, or they want a full inner shell. That's what they want. Okay, so if you think back to when we did electron configuration, okay, think back for just a second, and you look at these elements like in period 2, right? You have 2 s electrons and 6 p electrons. 2 in the s orbital and 6 in the p orbital gives us a total of 8 electrons. Agreed? Think back to when we did electron configurations. You had 2 in the s orbitals and 6 in the p orbitals. So that together, that shell gives us 8 electrons. That's what all atoms want. They want 8 electrons, or they want a full shell. So if you think about group 1 elements, let's look at lithium. Okay, here's lithium. It's got 1 shell, and then in its second level, it's got 1 outer electron. So is it easier for lithium to gather in 7 electrons to fill up this shell? Or is it easier for them to just give away 1? It's easier for them to give away 1 electron, which gives them a full inner shell, than to gather 7 more. Does that part make sense? It's much easier for them to give away that 1 electron than to gather in 7 more. So if I look at lithium, lithium has 3 protons, and it started with 3 electrons. If it gave away its outer electron, now it only has 2 electrons. Okay, but it still has 3 protons. So what charge does that give us for lithium? It gives us a +1 charge. Does that make sense? What charge do you see on your periodic table of ions for lithium? +1, right? It matches exactly what we did. Okay, so lithium is most comfortable giving away that outer shell electron rather than taking in 7 more. Right? Think about it. It's easier to give away 1 thing than to try to collect 7 more. Okay? Does that concept make sense? Okay, the same thing happens with the group 2 elements. If you look at magnesium, magnesium usually has 12 protons and 12 electrons, right? If it's a neutral charge, it's got 12 of each. So magnesium has an inner shell, another inner shell, and its third level, it's got 2 outer electrons, right? Do we agree with that? Magnesium's in the 3rd period, so it's got 3 shells of electrons. In its outermost shell, it has 2 because it's in the 2nd group. Okay? So is it easier? Okay, so that was our review with valence electrons. Now we're going to start naming. Okay? So we're going to name something first called monatomic ions. And monatomic ions are really easy to name because how many atoms are usually in a monatomic ion? How many atoms would you guess? Yeah, these are single atoms with a charge. Right, that's all monatomic ions are. They're single atoms with a charge. And naming them is really, really easy. Okay, the rules for naming monatomic ions is that an anion or a negative charge ends in IDE. It ends in IDE. So if you have an atom that ends in IDE, that means you know that you're talking about the charged version of it. Okay? So instead of oxygen, right, oxygen is just O, but oxide is O minus 2 with its charge. Okay? So there's a difference between those based on the name itself. Right? You use the root of the word and then you end it in IDE. That tells you we're looking at the negative version of that. Okay, does that make sense? So this oxygen has a neutral charge, right? Same number of protons and electrons. This oxygen is our charged particle, so it's got 2 extra electrons because it's a -2 charge. Okay. So that's the rule for anions. Cations just get to keep their regular name. There's nothing that changes about them. So they're really easy to name. So do you see all of the positively charged atoms just keep their regular element name, right? There's no way to differentiate if you're talking about the charged version or the non-charged version, so that's a little bit tricky. But sodium is the same whether it's 0 or +1. Right? It's still called sodium. Okay, so if you look at your periodic table of ions, all of your cations are their regular name, and all of the anions end in IDE. Okay, so they only end in IDE when they're charged. Okay. Questions about that? Okay, monatomic ions, easy. Next is something called polyatomic ions. Okay, what do you think poly means? Polyatomic ions are different than monatomic ions because they have more than one or many atoms. Okay, that make an ion. They have many atoms that together. Okay, carbonate. CO3 minus 2. Do we see that on your, in the table? You see carbonate on there? Okay, carbonate CO3 minus 2. So what's saying is that a carbon atom bonds to 3 oxygen atoms, and the total number of electrons within that compound give us a -2 charge. Okay, the electrons don't balance the protons. There's 2 extra electrons. And so we'll use these polyatomic ions to build bigger compounds. Okay? But the thing I want you to notice about naming polyatomic ions is that they each basically have their own name, right? You don't change their name at all. They are given a name. And usually if they end in ATE, that means they have oxygens attached to them. Okay? Oxygens attached usually means that it ends in ATE. Okay? I want you to look at nitrate. I want you to find nitrate on there. Nitrate is NO3 minus 1. And then what's the one right below it? Nitrite. And what is the formula for nitrite? NO2 minus 1. Okay, so do you see the difference between nitrate and nitrite? The only difference is that you lost 1 oxygen. So to go from an 8 to an ite, all you do is subtract 1 oxygen. That's it. The charge stays the same. Everything else stays the same. But to go from 8 to ite means you lose 1 oxygen. So I would write this down. Because there might be times where I ask you to memorize phosphate and sulfate and whatever, okay? Then you would automatically know what phosphite is and what sulfite is and blah, 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 okay? That's just kind of a little rule you can use. So if you know the nitrate and carbonate and phosphate or whatever, you can just subtract 1 oxygen and then you know another polyatomic ion, okay? So the rule to go from 8 to ite is that you just lose 1 oxygen. Charge stays the same. Everything else is the same. Okay? Something that I want you to notice is that the ending 8 doesn't always mean 3 oxygens. Okay? Because if you look at like sulfate, it's 4 oxygens, and phosphate is 4 oxygens. A carbonate's 3 oxygens. So I don't want you to try to memorize that 8 means 3 oxygens or 8 means whatever. Okay, you have to know what that is and then you can subtract 1. Does that kind of make sense? Okay. All right, now we're finally going to get into building compounds. We're going to start with binary compounds. Alright, so binary compounds, 2 types of atoms, has to have an overall neutral charge. We're going to try a combination between magnesium and bromide. Okay, we're going to build a compound between magnesium and bromide. Okay. The first thing that we want to do when we build a compound is write out each individual element with their charge. So each ion with its charge. So magnesium has what charge? Find magnesium on your periodic table of ions and tell me what's the charge for it. +2. Okay, and what's bromide's charge? -1. So we need these charges to equal 0. So right now, if I just totaled up our charges, I have 2 positive charges and 1 negative charge. What do I need to get myself to a 0? To an overall charge of 0, what do I need to do? Do I add a magnesium? Do I add a bromine? Do I add 2 bromines? What do I have to do? Yeah, Abby. Add another bromide, right? So if I have now 2 bromides that each have a -1 charge, that now gives me a -2 and a +2, which means my overall charge is 0. Agree? Okay, so the way I write my final answer is I have 1 magnesium and 2 bromides. MgBr2. Okay, if there's a 1 that goes here, right, I only need 1 magnesium, I leave that off. You don't have to include that 1. Okay, so by having no subscript, that tells us that there's a 1 there. So MgBr2 is our final compound, and the final written name for that is just magnesium bromide. That's it. The written name for these compounds is really easy. It's just the cation name and then the anion name. That's it. Okay. Let's try another one. Let's try a combination between potassium and phosphide. Potassium and phosphide. Okay, the name for this molecule would be potassium phosphide. Okay, so let's look at each of our charges. Potassium has a charge of +1, right? If there's no number there, it just says plus, that just means +1. Okay, so it has a charge of +1. Phosphide has a charge of -3. Okay, so which one do we need to adjust to get ourselves to a neutral charge? We need to adjust the potassium. And so what do we need to do to that to get it to be a neutral? We need to add how many potassiums? I need to add 2 more. So now if I balance my charges, I'm at +3 and -3, so that gives me a 0 charge. That's good. So our final compound is K3P. Right? Do I need to put the 1 right there? No. I leave that 1 off. Okay? If there is no subscript, that means we're assuming there's a 1 right there. Okay. Questions so far about how we're balancing them and putting them together. So our final formula is this, and the written name for it is potassium phosphide. It is really important that for all chemical compounds, we are looking at building them from left to right on the periodic table. Okay, so the cation always comes first, then the anion. Okay, so potassium is further left on the periodic table. It's a cation. It comes first, then the anion. So if you're in doubt of which one needs to go first, right, always follow the name, number 1. Number 2, you go from left to right on the periodic table. Okay? I didn't include this at the beginning, and I don't know why I forgot to do that, but these compounds are ionic compounds. This is a specific set of naming rules for ionic compounds. So you might want to put that kind of at the beginning of this naming section. These are ionic compounds, and so these rules that we're doing are for ionic compounds. And so ionic compounds are always between a metal and a nonmetal. Sorry, I left that off earlier. A metal and a nonmetal. Or you can think of it as a cation and an anion. Okay, a positive charge and a negative charge. So ionic compounds, these ones we're doing today, are always going to be between a positively charged particle and a negatively charged particle. Okay, we'll get to later doing ones that don't follow that rule. Okay, but all of these are ionic compounds. All right, let's try a combination between aluminum and oxide. Okay, which would be called aluminum oxide. All right, what's the charge for aluminum? +3. And what's the charge for oxide? -2. Okay, so this is a little bit more difficult to see what has to happen, right? It's not as easy because one of them's not a 1 charge, right? When it's a 1 charge, it's easy to just, tally them up, tack them on, whatever. But here it's a little bit more difficult. So if I add an aluminum, right now my charges are at +3 and -2. That doesn't give me a neutral. Right? So I've got to adjust both of them, right? Possibly one, but most likely both of them. So let's see what happens if I add an aluminum. What's that make my charge? +6 for my positives and -2. So now what can I do? Right? If I add another oxygen, now I'm at -4. So now I need another oxygen, which gives me to -6. And so that gives me an overall neutral charge. Does that make sense how you build that up? Right, you're essentially finding the least common multiple between those charges. Right, I think that's what it's called, least common multiple. Between a 3 and a 2, right, 6 was our least. We don't even care about the 6. We just care about the fact that it gets us to the right, a neutral charge. So that means we're looking at Al2O3, right? We needed 2 aluminums and 3 oxygens in order to balance out those charges. Okay, questions about that so far? Now I'm going to show you a much shorter method to get there. Okay? So I want you to look at the same example. Aluminum and oxide. Al is +3, O is -2. This is something called the crisscross method. Okay, this is called the crisscross method. And what happens is that we disregard the plus and the minus, and we crisscross them down, which means our compound is Al2O3. Isn't that exactly what we just came up with by balancing the charges? Yeah, it's exactly the same thing, but it took us a lot less time. Okay, so this method will work like 98% of the time. Okay, I'm going to show you the couple exceptions in which it might not, but this will work like a lot of the time. Okay, this crisscross method will. Okay, so all you do is disregard the plus and the minus, and you cross them down. If you still feel more comfortable just balancing the charges, that's great. And if you can see it right off the bat, that's great. But this crisscross method will work a lot. Okay, questions about that so far? Okay, let's try this one. I want to do manganese +4. I'm going to use the +4 version, and sulfide -2. So manganese is here in the transition metals, right in the middle, and I chose the +4 version of manganese. So I said Mn +4 and S -2. So we're going to look at this kind of both ways. Okay. First way we're going to look at is the crisscross method, because I think most of you will use that. Disregard the plus and the minus, crisscross them down, and that gives us Mn2S4, right? Okay, if we look at them just in terms of charges, Mn +4 and S -2, how many sulfides do I need to balance out my magnesium? Does that work just like that? right? A +4 and now a -4. So that leaves me with MnS2. These two compounds are not the same, right? What needs to happen to this one to get it to look like this? We reduce these down, right? You see a 2 and a 4. Those are both reducible by 2. Okay, so in an ionic compound, you have got to have reduced subscripts. Okay, so if they can all be reduced by the same number, which they can, that should happen in ionic compounds. Okay, we have to reduce those down. Okay, because the chemical formula, right, tells us the relative number of ions or relative number of atoms, so we want the most reduced version. So that's the situation in which the crisscross method can hurt you just a tiny bit, right, if you forget to reduce that at the end. Okay, so ionic compounds must be reduced. How are we feeling about naming our compounds? Pretty good? You want to try some on your own? Okay, so I'm going to give you a list of about 3 or 4. Some of them I'm going to give you the written name, and some of them I'm going to give you the formula. So you have to give the opposite. Okay? First one, let's do... Excuse me. All right, rubidium nitride. You're going to give me the chemical formula. I'm going to put a couple other up here. If I give you the formula, you're going to give me the name. Okay, so you've got 3 problems up here. Give me the formula, then the name, then the formula. RB3N. Raise your hand if you agree. That's what you had. Perfect. Rubidium is a +1. Nitride is a -3. So if we balance charges, we need 3 rubidiums to balance that charge, or we can crisscross down. Perfect. Next one, written name. Dawson, what'd you have? Aluminum sulfide. That's it. Perfect. Written names for these are super easy. Just name the cation and then name the anion. That's it. Aluminum sulfide. Okay, last one, magnesium oxide. Any volunteers? Yeah, Tim, what'd you have? MgO, like that? Raise your hand if you agree. Good. How many of you had it like this? Mg2O2. Right? Why is that no good? Got to reduce that. So we've got a 2 and a 2, so we have to reduce that back down. Right? Magnesium's a -2, oxygen's a +2, so automatically that tells us it should be a 1-to-1 ratio, right? They balance right together. Called lithium carbonate. Lithium carbonate. Okay? Look on in your box for carbonate. Find out what that is, right? If it has an 8, that's a really good indication that it's a polyatomic ion. It's not on your periodic table, it's in that box. Okay, so lithium is a +1. Carbonate is CO3 -2. Okay, did you find that in your box? Okay. So we can use the crisscross method, and that works fine. Or we can balance charges, it doesn't matter. But if I use my crisscross method to put them together, I disregard my plus minus, and I crisscross them, which means Li2CO3 1, right? What happens if there's that 1 there? I leave it out, right? I don't include the 1. So this tells me I need 2 lithiums and 1 of these carbonate molecules. Just one of the carbonate, okay? We are going to have to use parentheses if there's more than one of those polyatomic ions, but in this case, there's not more than one, so you don't have to include the parentheses, okay? So final answer looks just like this. Li2CO3. Okay, and it would be called lithium carbonate, right? Polyatomic ions keep their name. Polyatomic ions keep their name, okay? Second thing that I want you to point out is that we would never adjust the CO3. This subscript never changes, and it is not reducible. So if a polyatomic ion has a subscript, it is not reducible. Okay, you leave that alone. All right, let's try another one. Oops, magnesium nitrate. Magnesium nitrate. So as we crisscross them down, you need to understand, right, we don't adjust the 3 in nitrate at all, right? Nitrate stays NO3. So as we crisscross, we disregard the charge, and we say Mg1NO3 2, right? But the 1 gets left off because we only need 1 magnesium and we leave that off. We need to show that this 2 applies to the whole nitrate compound, which is when we add parentheses. Okay, just like when you calculate molar mass and you have something outside the parentheses, you know it distributes to the oxygen and the nitrogen. Right? The same thing applies here. We don't just need 2 more oxygens, we need 2 of the whole nitrate molecule. So that's why we put parentheses. Okay? So you might want to write that at the bottom. We use parentheses when you need more than one of a polyatomic ion. Okay? You use parentheses when you need more than one of a polyatomic ion, right? That's my little shorthand for that. Okay, what questions do we have? On your in your box, is there one called hydroxide? Do you see hydroxide? OH minus 1? Okay, I want to try one with hydroxide. So, aluminum hydroxide. Aluminum hydroxide. Aluminum is Al. Hydroxide is OH minus 1. If you just look at the charges themselves, you should know, you should be able to see that we need 3 hydroxides, right, to balance aluminum. It works the same way when we crisscross. So disregard our charge, crisscross them down. AlOH3. A lot of you will just want to leave it like that. AlOH3. Why is this wrong? Why does this formula look incorrect? Or how many of you just think it looks right? Right? This one is incorrect. Abby, tell me why. No parentheses. So without parentheses, what we're saying is that we only want 3 hydrogens. But that's not the case. We need 3 OHs. So to fix that, we add that parentheses to say we have this OH molecule and we need 3 of them. Okay? So if you drew out the molecule, which you don't need to do, it would look like this. Al, OH, OH, OH. Right? But if we drew it the other way, AlOH3, just like this, it would be Al bonded to an O, bonded to 3 hydrogens. Right? That looks a lot different than that molecule. Right? They mean 2 totally different things. So you need to make sure that if you need more than one of a polyatomic ion, you're using that parenthesis. Okay? Questions about that?